In the polar seas, where ice meets open water, a species is disappearing faster than we can study it. Lapras, the transport Pokémon, once filled these frigid channels with song. Now their numbers collapse. Each calf faces a gauntlet of thermal stress, starvation, failed migrations, and seas warming faster than evolution can adapt. This is not a story of strength, it is a story of fragility, of a life cycle so precisely tuned to cold that even small shifts become lethal. To know Lapras is to witness a species balanced on the edge of silence. In the sheltered fjords of the polar rim, where glacial walls dampen ocean swells and drifting ice creates pockets of stillness, Lapras calves enter the world. These are not arbitrary nurseries. They are chosen for precise hydrological reasons. Open seas would kill a newborn within hours. The violent churn of unprotected currents, the thermal drain of deep polar water, the endless motion that exhausts undeveloped muscle, none of it survivable. Protected inlets offer calm. They offer relative warmth where shallow water absorbs brief summer light. They offer proximity to the ice edge, where nutrient upwelling sustains the plankton blooms that will eventually feed the calf. A female in labor seeks these conditions instinctively. Guided by acoustic memory and temperature gradients, she has tracked across decades of migration. The birth itself is rapid. The calf emerges tail first, already needing to swim. In these first moments, surrounded by cold and silence, survival is only a possibility. A newborn Lapras weighs roughly 90 kilograms. Its body is soft, its shell plates thin and pliable, its flippers underdeveloped. The first challenge is not predation, it is physics. The calf must float. Buoyancy in marine mammals depends on the interplay between body density, fat reserves, and lung capacity. In Lapras neonates, none of these systems are fully operational. The blubber layer is minimal, the lungs are small and inefficient. The dense cartilage that will later harden into a protective shell currently drags the body downward. Without intervention, the calf sinks. Mothers compensate by positioning themselves beneath the newborn, lifting it toward the surface, nudging it into breathing rhythms. Over the first weeks, the calf learns to control inhalation depth, to hold air in ways that counteract its own weight. Flipper coordination follows. Muscle memory builds. The calves that fail to stabilize their buoyancy within the critical first days do not survive. They sink, they exhaust, they drown. There is no rescue. Polar seas drain heat from living tissue with ruthless efficiency. Adult Lapras endure this through layered insulation, controlled blood flow, and metabolic heat generation. Calves possess none of these defenses. Their blubber is thin. Their circulatory systems have not yet developed the counter-current heat exchangers that prevent warmth from escaping through flippers and fins. Exposed alone, a juvenile would lose core temperature within minutes. The solution is physical contact. Mothers keep calves pressed against their underbellies, positioned in the warmest microclimate their bodies can provide. When resting, adults curl around their young, creating thermal shelters from their own mass. In groups, multiple adults may rotate shielding duties, allowing mothers to feed while aunts or elder siblings maintain calf warmth. This dependency is absolute. A calf separated from the group in frigid water faces hypothermia before it faces hunger. The margin between survival and cold death is measured in proximity. Without contact, warmth disappears faster than hunger ever could. For the first several months, a Lapras calf survives entirely on maternal milk. This is not the thin fluid of temperate mammals. It is a dense, fat-rich concentrate designed to build blubber as rapidly as possible. The nutritional density is extraordinary, nearly 40% fat by weight, delivering calories in volumes the calf's stomach could not otherwise process. But milk cannot last. As the calf grows, its metabolic demands outpace what nursing can provide. The weaning process begins gradually, guided by the mother's feeding behavior. Calves observe prey capture. They mouth small organisms, swallowing little but stimulating digestive changes. The gut lining thickens. Enzyme production shifts from lactose processing to protein and lipid breakdown. New microbial colonies establish in the intestinal tract, enabling digestion of krill, fish, and the gelatinous filter feeders that dominate polar food webs. This transition is dangerous. Calves that wean too early lack the gut development to extract sufficient nutrients. Those that wean too late fail to build the foraging instincts they will need. The window is narrow. The cost of error is starvation. As months pass, the soft-bodied calf begins its transformation into something built for endurance. Shell plates harden. What was once pliable cartilage mineralizes into dense, curved armor that will eventually deflect predator strikes and insulate against deep water pressure. Beneath the shell, muscle fibers lengthen and thicken, layering in patterns optimized for sustained swimming rather than bursts of speed. The flippers elongate, their edges sharpen into more efficient hydrofoils, reducing drag with each stroke. Body contour changes as well. The rounded, buoyant shape of infancy gives way to a streamlined profile where fat deposits concentrate along the core rather than the extremities. This is not cosmetic. It is engineering. A juvenile that fails to develop proper hydrodynamics will burn excess energy fighting water resistance, energy it cannot afford to lose in seas where food is patchy and distances are vast. By the end of the first year, a surviving juvenile has doubled its birth weight and fundamentally reshaped its body. Strength arrives just in time for the ocean to test it. The first long migration is a crucible. Juvenile Lapras that have spent their early lives in sheltered fjords must now enter open ocean, following adults across hundreds of kilometers of current, ice, and empty water. This is not instinct alone. It is learned behavior transmitted across generations. Adolescents swim in the wake of experienced adults, drafting on their movements, absorbing information encoded in subtle shifts of direction and speed. They learn to read temperature gradients, to recognize the acoustic signatures of distant ice shelves, to feel the pressure changes that signal approaching storms. Many fail. Some lose contact with the group in low visibility conditions and cannot relocate the herd. Others misjudge energy reserves and exhaust themselves before reaching feeding grounds. The polar ocean does not forgive navigational error. Those that complete the first migration carry its lessons forward. They have crossed from dependence to competence. They have become migrants. Adulthood in Lapras is defined by thermal independence. The biological systems that were absent or underdeveloped in youth now function at full capacity. Blubber layers have thickened to provide passive insulation even in the coldest waters. Blood vessels in the flippers and tail have restructured into counter-current exchangers, arteries wrapped tightly around veins, warming returning blood before it reaches the core. Metabolic rate can now shift dynamically, ramping upward to generate heat during deep dives, throttling downward during rest to conserve energy. These adaptations allow what was once impossible, sustained existence in water that would kill most organisms within minutes. An adult Lapras can dive to crushing depths, remain submerged for extended periods, and surface with core temperature intact. It can cross polar seas in winter, feeding beneath ice sheets where prey concentrates. Survival is no longer borrowed. It is regulated or lost. The polar ocean is vast, dark, and featureless to visual perception. Lapras navigate it through sound. Adults produce low-frequency vocalizations that travel enormous distances through cold, dense water, wavelengths so long they bend around obstacles and propagate across entire ocean basins. These calls serve multiple functions. They maintain contact between scattered group members. They signal location to potential mates during breeding season. They may encode information about current conditions, ice boundaries, and prey concentrations, though the full complexity of Lapras communication remains poorly understood. What is clear is that acoustic awareness defines adult spatial behavior. Lapras do not wander, they orient. They track the positions of others, adjusting their own movements in response to calls received hours or days prior, In waters where visibility drops to near zero, sound replaces sight entirely. A silent Lapras is a lost Lapras. Those that sing remain connected to a network stretched across the frozen sea. Lapras breed slowly. Females do not reach reproductive maturity until well into their second decade, and even then, breeding occurs only when conditions align. Body fat reserves must exceed a critical threshold. Migratory routes must remain stable enough to guarantee access to calving grounds. Environmental stressors like ice loss or prey scarcity can delay reproduction for years. When breeding does occur, the investment is total. A single calf gestates for nearly a year, demands constant thermal shielding after birth, and requires parental guidance for the better part of a decade before achieving independence. This is not inefficiency. It is strategy. In unstable environments, producing many fragile offspring is a losing gamble. Producing few, robust, well-taught offspring offers better odds, but it also means that population recovery, once numbers decline, is agonizingly slow. Each lost calf represents years of irreplaceable investment. A fully mature Lapras is more than an individual. It is a structural element of the polar food web. Its feeding redistributes nutrients across vertical and horizontal gradients. Its movements connect distant ecosystems. Its carcass, when death finally comes, delivers organic matter to the deep ocean floor, feeding communities that never see sunlight. Remove Lapras, and the architecture of the cold sea simplifies. Prey species lose predation pressure, nutrient cycles stall, the deep benthos starves. And now, removal is underway. Warming seas shrink the ice edges where calving occurs. Shifting currents disrupt migratory routes encoded across generations. Prey populations destabilize. Each stage of the Lapras life cycle, from fragile birth to hard-won adulthood, depends on conditions that no longer hold. The frozen tides are thawing. The song is growing faint.